Okay, good day and welcome to this joint webinar between two ICOLD committees, the Young Professionals and also Committee L, Tailings and Waste Lagoons. My name's Jared Coffey. I'll be hosting this evening and also moderating the question and answer sessions. I actually am from Committee L at ICOLD, Tailings and Waste Lagoons, where I'm the Young Professionals representative from Australia and ANCOLD. It's actually the second joint webinar we've had between these groups in 2023. I think it was March. We explored opportunities and challenges of a career in tailings, and tonight we're going to expand on that just a little bit. Firstly, we're going to be focusing on governance, and that's going to be centered around the global industry standard on tailings management, which I imagine probably all of you are already aware of, and specifically the formation of the Global Tailings Management Institute. I think many of you will have seen some announcements earlier this year on the Institute's formation, and we're going to hear a little bit more about how work's progressed since tonight. Another important topic in the tailings industry, and is also reflected in GISTM, is risk-informed decision-making. That's also spoken about in Bulletin 194, published by ICOLD quite recently, although it has been on the website as a preprint for some time. One specific challenge with risk-informed decision-making, and especially setting design criteria is the issue of brittleness. Like many of you probably know, that it's not so easy to be able to monitor for such types of failure modes, and so it puts a real emphasis on the design phase, the testing, and also interpretation of that data that informs the design. So we're very lucky to be presented by two esteemed speakers tonight, Dr. Emma Gagen, Director Data and Research at International Council on Mining and Metals, or ICMM, as many of you will probably know them, and also Dr. David Reid, Principal Engineer at Red Earth Engineering and the head of the Geosyntec REE lab for just about 9 months now. I'll let each of them introduce themselves a little bit more as we get started on each of the presentations. Just first, before we jump into that, a couple of housekeeping issues. If you wish to ask a question, please feel free to do so via the Q&A function or the chat function. I'm not sure what exactly it's called, but I'm sure you know it in the top right-hand corner of your screen. I will do my best to get to as many questions as possible, but we will try to keep the session to 90 minutes. All of our speakers are in Australia, and it's going to be getting late into the evening, so we won't keep them for too long. At the conclusion, I'll also invite Matteo Clune to share a few messages about the ICOLD Young Professionals Committee and some of their activities. So sorry, I should have moved my slides as we're going through some of that. So there's the agenda there. I think I've pretty well summarised all that already. So without further ado, I will hand over to Emma to present on the GTMI. And Emma, please feel free to take control of the screen when you're ready.
Thanks, Jared. Thanks, Matteo. Thank you to the ICOLD for this invitation to present on the Global Tailings Management Institute, or GTMI. There will be a lot of abbreviations in this talk, but I think most of us are familiar with that in this industry at the moment. Before I get into the GTMI, I would like to introduce myself because most of you won't be familiar with me. I'm not a tailings face per se. But I oversee our tailings management work at ICMM as part of the portfolio, my portfolio, which also includes our data and research work. That's a new piece of work, this strategy, and materials stewardship facility, which is kind of like pollution policy. Before this, I was in our environment portfolio overseeing our water, closure and nature work. And so that's kind of how I found my way to tailings, through the closure route. My background is actually in microbiology and rehabilitation of mine sites. So I don't pretend to be an engineer, and hopefully no tricky engineering related questions. They can go to David after me. Thank you. But I'm going to introduce you a little bit to ICMM. I assume most of you don't get a chance to go into the deep dive about what ICMM does and where tailings fits within our work. So I did want to take that opportunity up front before diving into the Global Tailings Management Institute and its origin story, and then where we are now and where we're going next, which is super exciting. This is, I think, the pivotal year for the GTMI. So who's ICMM? We're a global sustainability leadership organisation bringing together about a third of the mining and metals sector So our 24 mining company members, they're listed on the slide here. And then we also have about 45 or 50 associations members, and they might be commodity associations, copper, lithium, manganese association, or they could be regional associations like the National Mining Association or Mining Institute or MAC, for example. All of them share our vision for a safe, just and sustainable world underpinned by responsibly produced minerals and metals. Through our reach with the company members, our standards are effected in more than 650 assets at more than 50 countries globally. Our mining principles are the foundation of ICMM membership. So it's not really possible for someone to just say, I'd like to be an ICMM member, can I pay a fee? There's a rigorous process around adhering to the mining principles that we've outlined, and a site level assurance and validation, and over a continual cycle against all of those commitments. There's 10 mining principles, and each of the sub-commitments under them are articulated on our website, or sometimes in more detail via position statements where there's a very clear subtopic that needs a deeper dive. But you can find out more about any of those on the website, everything from environmental performance through to social performance and governance. The tailings related principles are under mining principle number 6, which I'll dig into now. And it's actually our environmental performance portfolio. It includes commitments on climate, water, pollution, etc. But our commitments around designing, constructing, monitoring and decommissioning tailings facilities in line with good governance and international good practice are the foundation. You can see we have a couple of footnotes against the commitment there, and that includes taking a strong position that freshwater lake riverine disposal and shallow marine disposal is an absolute last resort. And the second footnote around our commitment to implementing the global industry standard on tailings management. But otherwise, kind of encapsulated in that very high level principle there. Where we exist as an organisation is to support our members deliver on those commitments. This is what it looks like on a page for us for the next 5 years. This is our strategy that just started in 2025 on how we're going to support our members deliver on their commitments on safety or climate or tailings, as you can see under the performance pillar of our work. We also have other parts of our work program that are around raising wider industry standards, so not the membership specifically, but outreach to other parts of the world or unreached areas of the sector, for example. That's primarily being achieved through the Consolidated Mining Standard Initiative. Happy to take questions offline on any of that work if it's of interest. There is a tailings chapter, and this will become the standard that replaces our mining principles in the future. Then there's a third piece of work that is around dialogue, engagement, communication and advocacy. And you can imagine tailings gets a feature in there as part of our outreach or showcasing member performance. But this is also policy engagement and the data work that I talked about that's new, this strategy. So it's not focused on tailings in particular, but tailings may get a feature in any of these pieces. So I hope that's a bit of a snapshot on where tailings fits for us as an organisation. It isn't something that we've started working on recently, however. So here's a kind of look back over the last 10 years, if you like. In 2016, our council, which is the 24 CEOs of the major mining companies that are our members, agreed to a position statement taking a very specific commitment around tailings governance. And that includes everything from change management, the whole life cycle from pre-fees through to closure, and articulating really specific requirements on accountability, competency planning, etc., emergency preparedness. We had, in parallel, a piece of work or an idea being birthed that it wasn't only about safety, however, and a couple of years later, Council also committed to a longer-term goal to do something really innovative and think about eliminating conventional tailings storage facilities completely. And this is articulated in what we call our tailings aspirational goal. It's a much longer term kind of vision, if you like, 10 to 15 year goal to innovate and think of ways to eliminate conventional tailings storage facilities. This is, I think, a really exciting piece of work that probably hasn't gained as much attention as it might have in a different set of previous 5 years, if you can think about that. But a really important piece of work about collaboration to reduce the hurdles and the activation energy for overcoming some of the challenges around implementing new technologies at scale, or rolling things out and piloting and testing things that we can do with the membership that you probably couldn't do if you were just one company alone. Some of those things are, really out of the box, like precision geology, precision sorting, precision mining, even to, reduce the amount of waste that we actually produce in the first place. And then some of it's at the other end of the spectrum where we're already doing some work and we're just looking to optimize or further improve. So waste valorization, for example, is there a way to eliminate tailings facilities by using the tailings for something else? It's a huge piece of work, actually, that also happens in that tailings innovation space. As you all know, 2019, the tragedy at Brumadinho happened, killing 272 people and catalysing massive change in our industry around tailings management. And so from here on, a lot of our focus then became on the response to that and the development of the standard, the global industry standard on tailings management, which I'll probably just call the standard. A month later, we'd committed to developing a new standard with the United Nations Environment Programme and the Principles for Responsible Investment. We co-convened a global tailings review led by Dr. Bruno Oberle, and that involved a huge amount of stakeholder engagement and consultation and development of a draft standard less than 6 months later that went out for public consultation. Incorporating the feedback from that global tailings review and public consultation period, the standard was launched in August 2020. Our members committed to implementing the 77 requirements of that standard for extreme and very high consequence classification facilities within 3 years, and the rest of their facilities within 5 years, which will be August this year. So you'll see we did, our members disclosed their conformance for the extreme and very high consequence classification facilities in 2023, and you'll see everything coming out for the remainder in about 2 weeks' time. As I alluded to earlier, we exist as an organisation to support our members deliver on their commitments, as well as raising wider industry performance. Our focus is to help our members implement the good practice that they've committed to and maintain the standards. So we worked really hard after the development of the standard with our members and with external stakeholders to develop guidance to really support the implementation of the standard. Some of this will be familiar to you. This is one of our most downloaded tools. All of our guidance is publicly available for non-members as well. So the Tailings Management Good Practice Guide was published in 2021 and really drills into the details of how to operationalise the principles of the GISTM. And that was developed by practitioners who are tailings leads in their company, for example. It wasn't a piece of work we just did at an arm's length with someone else. It was really birthed through the sweat and tears of our members on the ground trying to operationalise these principles. In parallel, we also launched or released the conformance protocols to support auditors to audit against the 77 requirements of the standard. And I'll come back to those later, but you may already be using them, some of you, in your day-to-day. Slow burn on that piece of work that I mentioned around the tailings aspirational goal. And in 2022, we released our tailings reduction roadmap, which kind of articulates the ripest opportunities for innovation and collaboration and advancing some of those out-of-the-box ideas to eliminate or completely reduce tailings facilities going forward. And that's also available on our website if you're interested. And the piece of work that we're doing, this strategy, it includes both tailings management support as well as this tailings innovation roadmap, trying to deliver some of the commitments there around accelerating innovation on tailings. In the background, the Global Tailings Review, when they convened in 2019, some of their recommendations, or one of their recommendations, was that an independent advisory panel needed to be established to support a long-term home for the standard once it was live. In 2021, United Nations Environment Programme and PRI and ICMM announced the formation of this independent advisory panel, and it was, I think, led by David Cooling, but also had input from stakeholders as well as industry representatives. And they took a couple of years to formulate ideas around what would a long-term credible home for the standard look like. They published their findings, or I don't think they actually made them public, but they shared their findings in 2023, and it announced, or UNEP and PRI announced the establishment of an institute that would become the home of the standard. It's taken us a couple of years since then, as the founding partners, to actually formulate a memorandum of incorporation, a way of working, to agree on long-term governance and ensure the long-term success of such an institute. So you can see the timelines are not fast, but I think this is the importance of a multi-stakeholder approach to this kind of work. It's better to get it right and to nut it out as we go than to rush and have something that either doesn't have credibility or won't get widespread uptake. So between 2023 and 2025, we as the founding partners, ICMM, UNEP and PRI, worked together to nut out those details, and we launched the GTMI, the Global Tailings Management Institute, earlier this year, which I'm super excited about. So in my portfolio at ICMM, under the tailings management work, also included this piece of work to see the GTMI fully functional, if you like. While it's been co-founded and established in South Africa, there's a lot of, administration and logistical details that probably no one's aware of until they try to start establishing an independent institute. So progress has been slow, or slower than I anticipated, and I had really hoped we would have had a public announcement this week before this presentation that I could kind of share a bit more info with you. But I will give you a sneak peek and say, keep your eyes peeled before Friday. I think you'll see a pretty key announcement coming out from the GTMI. But what you will have seen already is that it's an independent multi-stakeholder governed organisation. So it has its own CEO, or will have its own CEO. It'll have an independent board, a multi-stakeholder governed board, and it's incorporated in South Africa. It was really important to all the founding partners that the Institute, wherever it ended up with its home, had it in a place that had strong tailings background with and a presence in the global south. And South Africa seemed like a reasonable choice for that when we were considering where to have this thing long term. Its goal is the same as the goal of the standard, the same thing we all want, to achieve zero harm to people and the environment from tailings facilities, doing that through pretty much implementation, adoption and certification against the GISTM. Their core function, delivering on that vision, is to manage the assurance framework around the GISTM. So one doesn't exist. We had published our conformance protocols a couple of years earlier, but an independent assurance framework with auditors that are accredited and certified doesn't yet exist, will exist with the GTMI. So that's their core function, to manage or develop and then manage that assurance framework. On the side, they'll also have a key role in supporting wide uptake of the GISTM outside the ICMM membership, so widely across the industry, to facilitate knowledge sharing, best practices, capacity building, as well as disclosure of auditing outcomes. And so that was one of the key requirements or recommendations from the Global Tailings Review, that for this institute to have credibility, it needed to also have transparency for stakeholders to be able to see disclosure outcomes against the GISTM. So that's going to be a really unique, I think, powerful feature of the GTMI. It's a not-for-profit organisation. I don't think it's in a later slide, but people can become a signatory by paying a fee, and it should be a flat fee based on the size of the company, size being determined by number of TSFs. So less than 10 TSFs, you might be a small company, more than 10, you might be a big company, flat fee based on that. But the idea is not for that to become a money-making organisation, but for the funds to go back into the assurance accreditation scheme and the industry outreach and knowledge sharing for the facility. The multi-stakeholder board that we've written into the Memorandum of Incorporation has 9 members on it, representatives from the mining industry, affected communities, Indigenous peoples, the others that you can see on the screen. This is part of the reason why an initiative like this takes such a long time to get off the ground. You can imagine how can we bring different voices and different perspectives from all these different groups and have a constructive and a productive board that's going to have a long-term or set the long-term future for the Institute going forward. We've really taken our time since the call for applications from the board to interview and interview again and ensure we've got the right mix of people on the board. So that process is very much in train, and I anticipate an announcement about the board later this week. Later, after the board is established and a CEO is recruited and in place, a technical committee will be established, and their role is to oversee any technical related elements that come to the GTMI. So whether it's questions about the standard or reviews of the standard, the technical committee will be individuals that are a lot more tailings focused than necessarily some of the representatives on the board, who all have an interest in tailings and are very well connected, but aren't necessarily engineers, if you like. So that there will be those two committees function, or the board and the committee functioning in parallel with quite different scope. As mentioned, you should see a board announcement soon. We're also in progress searching for the first CEO for the GTMI. He or she may choose to appoint a CTO. There is capacity for that in the structure, the governance structure. If they want to do that, there could be a CTO soon after, and the technical committee establishment will be very imminent. I believe one of the first activities after the board is established. So keep an eye out for any of those things as well. If those are of interest to you, you can subscribe on the GTMI website for updates via LinkedIn, or they'll come into your email inbox. But if anyone is interested in applying for a position on the committee or recommending someone, keep an eye out via the newsletter. After those kind of formalities and ensuring that the GTMI is set up for success, we're looking for mining companies to become signatories, and anyone who's not a mining company could become a supporter. And I'll explain the difference between those two in the next slide. Signatories are anyone who has responsibility for a tailings facility can become a signatory of the GTMI, and that's a commitment to responsible tailings management, to conformance with the GISTM, as well as knowledge sharing and capacity building more generally. That's the primary thing. If you want to become a signatory, it's a commitment to implementing the GISTM and fully disclosing transparently outcomes from the conformance against that. It's also about stakeholder engagement, I think, and being able to communicate that you are a GTMI signatory, therefore you should be expected to be operating at a different level to others who are not GTMI signatories, and the founders anticipate this should improve relationships or give some more social license to operate, improve relationships with regulators, potentially investor confidence, insurance coverage, etc. So kind of that's the business case articulation, if you like. It's not just that GISTM is the right thing to do. There should become a distinguisher in the future that someone can say, I'm a GTMI signatory, my outcomes are transparently disclosed on the website, therefore you can trust what I'm doing and have confidence in me if you want to invest or approve a permit, or if you're a community nearby. That's kind of the origin and the idea. If you're not responsible for or have operational responsibility for a tailings facility, you're still able to support the GTMI. And supporters have a role, for example, in fostering knowledge. They might want to host a roundtable or facilitate wider industry uptake, or create the connections that are necessary for the regulator to dialogue with the GTMI. You know, we don't have a limit on this, but it's just to signal that GTMI support doesn't only involve the financial commitment and the financial contribution and the commitment to the standard. It can be from the rest of the community around tailings as well. And so I'd encourage you, if you're a consultant or if you're an interested party, think of the ways that you might be able to support the GTMI and its mission through some of this capacity building, knowledge sharing, relationship support. And to become a signatory, or a supporter, I think it's the same. I would say the same thing at the moment. Please sign up to the newsletter on the website to get notifications about that. As the GTMI gets legs and becomes a more functional organisation, you'll be getting more specific information about what membership looks like, if you're or not membership, but what becoming a signatory looks like and the fee structure and those kind of things. But there's a number of resolutions the board has to pass for any of those things to become operational. So I would say subscribe to the website for the latest updates on any of these things. That's pretty much it. I think I probably went a little too fast, so there may be plenty of questions if I've skipped over things. But what I wanted to summarise is that tailings management has and continues to be a core part of our work. It wasn't something that just started when Brumadinho happened, and it isn't something that's just going to finish. It involves our management work as well as our innovation work. We've worked hard with UNEP and PRI over the last few years to co-found the GTMI. It's incorporated in South Africa, has a board imminent, and will soon be fully functional. Keep an eye out. This thing's going to be a game changer and the long-term home for the GISTM. It will oversee conformance with the standard, transparency of disclosure outcomes, and wider industry, take responsibility for wider industry uptake of the standard. As I mentioned, the board has been appointed almost, I can almost announce it, and the key executive positions will soon be filled. So please keep an eye out for the next steps, which would be how, if you're an operator, you can become a signatory, or if you're a consultant or other interested party, you could be a supporter of our work together. And that's all from me, Jared, if there are questions.
Yeah, thanks, Emma. Really appreciate you taking the time to update us today. And we only missed it by that much, hey? Maybe next time there'll be a little bit more to share, I guess. I'll give everyone a couple of minutes maybe to think about some more questions in the chat. Emma, one thing you didn't touch on was potential updates to the standard in future and how that would fit with the GTMI's responsibilities.
Yeah, great question. And I purposely didn't because I hoped someone might ask. I believe the Memorandum of Incorporation will become public once the board is fully functional. It should be up on our website. So you'll be able to see any of this information to fact check me then. But the founding partners want the GTMI to be fully independent and fully functional on its own. So when the board is in place and the CEO, we're kind of extricating ourselves and taking a back step. However, when there are ever decisions in the future from the board or recommendations, technical committee, whoever, to revisit or reopen or look at changes to the standard, the founding partners get called back in. So that's kind of the only time we would intervene again in this independent functioning entity in the future, and that would be if and when the standard is being reevaluated. I would say that I don't believe a core or a primary first step of the board or the technical committee is to open the standard. There's a lot they need to do around conformance, the assurance procedures, and then validation and how they're going to transparently disclose auditing outcomes. So I personally don't believe that reopening the standard is a first priority in terms of the priorities for the GTMI going forward. But we'll see once it's independently functioning what comes out.
Yeah, for sure. Thanks for that. We've got a few questions coming in. Would the GTMI provide a mechanism to review grievances from local stakeholders?
So there should be grievance mechanisms at a site level. And I think the same as we as an organisation take the approach, if somebody comes to us with a site-specific grievance, we try and direct them through the channels that are appropriate at the site level. Having said that, the GTMI is the place for people to raise their concerns, and they could connect with the board, or they could connect with whatever channel is created for the GTMI to engage with the regulator or affected communities in the future to raise their concerns if they've been consistent and they feel that they haven't been heard. I would say probably it's not supposed to be like a dumping ground or a complaints hotline or anything like that. But if there is a discrepancy between what a disclosed outcome or an auditing outcome and what someone's experiencing, then I imagine the GTMI is the home for that kind of question if it isn't being met at the site level through the regular channels.
Yeah. Another one here. Are there any plans to have GISTM combined or merged with other standards, Coppermark or TSM, for example?
Thank you, whoever has asked that. I love talking about the Consolidated Mining Standard Initiative. That's my second favourite topic at the moment. So ICMM is embarking on an initiative to merge our standards with those from Coppermark, World Gold Council and Max TSM towards sustainable mining. This is an initiative we've also been on for a number of years, and it includes developing a single standard to denoise the complexity in the standard space right now. And the idea was to take the best of the 4 standards to a single consolidated standard, so to raise the bar rather than have any dilution effect. There are 24 performance areas. One of those performance areas is tailings. The draft, it went for public consultation in the end of last year, so that's publicly available. It's being revised at the moment in response to the public consultation. What I've seen of the revised draft chapter on tailings does allow for some flexibility. I don't think it's that different to the one that went out in December, if you do want to check it, but to allow for equivalency, I think is probably the right word, between one standard or another. And it makes specific reference to the GTMI, because obviously the GTMI wasn't formalised and finished by the time the draft was being worked out. So I think there might be scope to update that particular chapter depending on what comes out of the GTMI going forward as well. So at the moment, the way we've seen the standards landscape is that we will allow some equivalency in the standards that we're consolidating, with the caveat that maybe that chapter gets revisited when the GTMI is more mature.
Yeah. Okay, there's only one more question. So this is your last chance, everyone, if you want to sneak something in. I think this maybe has something to do with some of the supporter role that you were talking about in the presentation. Is there any consideration to have a board or team of young engineers in the industry? And I presume that is to sort of play an advisory role to the GTMI.
We haven't articulated anything that formal in the Memorandum of Incorporation, but I think that's a cool idea. There will be, and we're yet to see how the board and the CEO want to roll this out, but there will be some kind of formal engagement mechanism of the GTMI with interested stakeholders or affected stakeholders or regulators. And so workforce is one of those, and workforce is reflected in the composition of the board, not specific to young workforce, but just workforce. So I would say that there could be an opportunity through a formal mechanism of engagement with workforce, and or if young representatives would like to make a connection with that board member who's representing the workforce and bring their views that way, I believe that would be welcomed. So yeah, I'd say keep an eye out for the board announcement, get familiar with who those people are, wait to hear what the formal channels of communication with the organisation as a whole are, and or if you can have connections with any of the individual members on the board.
Really love that question. Very on theme for tonight. So one last one before we let you go, Emma. I don't know whether you can comment on this too much, but what's the standpoint of ICMM to advocate on GISTM for non-ICMM members?
Our advocacy efforts around raising wider industry standards are primarily being delivered through the Consolidated Mining Standard Initiative at the moment. So you might remember I said earlier, we reach about 650 assets in more than 50 countries through our membership. We anticipate the Consolidated Mining Standard Initiative to reach many, many more, and it will do that through providing an on-ramp. So rather than just saying, here's the performance expectation, it's this high, if you can't meet it, too bad, it provides kind of a pathway for a progression from foundational performance to good performance to leading performance. And so we are really working hard to see that as the avenue for promoting wider industry uptake on all areas, tailings just being one of the chapters, but really anticipate that being a significant opportunity for non-ICMM members to improve their performance on tailings and other areas. So I actually think that's one of the most exciting things we're working on, as boring as standards can be. I think this has the potential to be a real game changer for reaching parts of the world that typically we haven't, or traditionally membership organisations haven't, because the bar's just been too high, too far, forget about it. Through the CMSI, we'll provide an on-ramp for people that want to start their standards journey and improve.
Yeah, it's there's lots happening still in this space in the tailings industry. It's exciting times for all of us, I think. we'll probably cut the questions there for Emma. Unfortunately, I can see a couple more rolling in, but David has got many, many slides I've seen, so we shall move on. Firstly, though, thank you so much, Emma. I know it's getting late where you are, but we all really appreciate it.
Thank you, Jared. I'm happy to take questions offline if people Google and want to email. Thanks.
Thank you. Okay, we will move on now to Dr. David Reid. I will let you introduce yourself, Dave, and your topic, assessing the brittleness of tailings, some common pitfalls and uncertainties.
Thanks, Jared. And I won't go, maybe I'm probably not going to present all those slides because I don't want to go crazy here. So yeah, good point. My name is David Reid. I'm a tailings engineer, principal tailings engineer at Red Earth Engineering in Perth. I've been back and forth from academia and consulting a little bit. And right now I'm running our laboratory facility called Relab, which is primarily focused on testing tailings for the mining industry. Let me just open up my vision. Okay, assume that's okay. All right, so assessing the brittleness of tailings, some common pitfalls and uncertainties. The main thing I want to talk about here is, so the idea, the concept that we're all working around, which is brittleness index, brittleness is really important and valuable, and it's a great insight. But I just want to share some areas where we can get ourselves in some trouble, because using this framework requires probably a step change in quality in some cases of how we measure some of these things. So that's kind of one of the purpose of today's talk. But before I get into the details, just for those of you that haven't seen it recently, brittleness index, which was first developed by Bishop in the 60s for drain situations, and then extended quickly to undrained testing, is this formula right here, where it allows you to quantify the amount of strength loss after a peak is achieved. So a brittleness index of 0 indicates no strength loss. A brittleness index of 1 is complete strength loss post-peak, and everything in between. Now, this was originally published in the 60s, and Bishop's not someone who really needs to worry about his H-index, but in the last 5-10 years is where you've really seen this hit another level of adoption and recognition as being a useful tool to quantify this. Now, the problem with brittleness is that when things are brittle, they can look like this. They can fail rather suddenly in some cases, and they can go a great distance, because the more strength something loses, the further it needs to travel to reestablish an equilibrium, if it even can. So this is what we're talking about, things that go a long distance, can cause a great deal of damage, and in many cases can do this with very little warning, particularly if that drop post-peak is steep and fast. In that case, the ability to have warning for this is very little. One of the reasons why we're so worried about this type of structure, brittle soils. Now, this brittleness index has been incorporated probably the place you're probably seeing it most often now is in the most recent ICOLD bulletin, which is really good because it sets the scene around this concept. It goes through a bunch of background about it it's a very good read. So it's really useful because it's got us talking about the right thing. Like I'd kind of argue that people spend a bit too much time worrying about whether something's liquefiable or not liquefiable, run an Adderberg limit check, stuff like that. That's almost a red herring. What really matters is how much strength does it lose post peak and how fast, because the Adderberg limits, while giving you some indication of that, are not really the key. Whether something's liquefiable or not is not the key answer or the key question. The key question is how brittle is it and how fast is that going to happen? Okay, so the ICOLD bulletin breaks this up into some different categories. That's not really the main point of today. You can read that. It explains it better than I can. The main thing I want to talk about today is that if you want to use this framework, which I think, of course, we all should be using and will be using, you need to be very good at measuring both the peak and that final residual value, right? Because if you can't capture how the soil is going to behave in situ in some reasonable way, then applying this kind of framework becomes more difficult, and in some cases could be misleading and dangerous if one is estimating these things in a not state of practice way and getting erroneous values. So that's the point of today, is just to go over some areas where I see issues happen around how you would capture the strengths you need and the stress strain results to make this kind of a conclusion. I just want to start at the beginning. This first one's gonna be lab. Most of it's lab based because that's kind of my home turf. And I want to start really basic with moist tamping, because even though a lot of people quite rightly don't like moist tamping, it's sometimes all we have for some of the situations we find ourselves in. We want to prepare tailings, say silt, very loose. Now, to do that, we don't really have any choices in terms of preparation technique other than forms of moist tamping right now. So we end up using moist tamping probably more than we deep down really want to be using it. But anyway, That's what you're going to see across the board in a lot of cases for good reason. Now, the thing about moist tamping is there seems to be a misconception that just a standard off-the-shelf procedure that everyone's using is going to produce something that's as brittle as in situ. And I want to be really cautious about that because as terrifying as it might sound, we're not sure that we can produce samples as loose in the lab as might exist in the field, which I know sounds kind of ridiculous, but the evidence that I see and that I see other people seem to agree with points that way. So let's just take a little journey through this particular sample. So I'm preparing a silt tailings here, nice and loose. That's the red dot. I'm going to confine it under about 20 kPa just so it doesn't collapse. And then make it as loose as I can. So about void ratio of 1.05-ish for this particular sample. That's as loose as I can probably make it, okay? Working really hard to make it loose. Now, when you prepare these samples, you then saturate them. Because unless you're doing something really cute and academic, usually you want a saturated sample. So then they collapse. They collapse a great deal. And that's okay. That's fine. That's just the loosest we can probably make it from this particular journey now in a saturated state. We generally want to be saturated because that's what we want to, the condition we typically want to test in. Now, it's this collapse that is actually what makes these kind of loose tests and obtaining the critical state line so challenging and why we use things like end of test freezing. But that's kind of for a different story. Let's just assume the void ratios are right here for the purpose of this presentation. You then might consolidate that sample to a particular mean effective stress, in this case, 300 kPa, for example. And then you might shear it from that particular state, which will tend to the critical state line. Okay. Now, this is a pretty common procedure people use across all the time now. You consolidate to a bunch of different stresses and then shear to the critical state line. Now, people have taken data like that and they've said, okay, how loose can I make it using moist tamping, which is the gray lines on the left. Well, I'll turn my pointer on to make this, to make this more easy to deal with. Okay, people will get a line like this using various types of moist tamped specimens, which is great, and they'll shear it and they'll get a critical state line like this. It's very common. And then they might look at these results and they might say, okay, the brittleness index, that thing that we were talking about at the beginning, is reducing with mean effective stress. Okay, the reason for that, and this is very common, there's two reasons. A, the critical state line is curved, so therefore the distance these tests need to move horizontally to get to the critical state line gets to be less and less distance, which makes something less brittle. It's losing less mean effective stress during shearing. And secondly, this line starts to converge on the critical state line. Typically, here I can get a much looser state than here, even above and beyond the curvature issue. Okay, so people have looked at this and said quite reasonably that at higher stresses, it looks like brittleness generally reduces, which is certainly a reasonable conclusion from this particular outcome set of tests. But one thing to be cautious about is we use moist tamping in the way that everyone uses it. We prepared a sample and we saturated it at about 20 kPa confining pressure. Okay, that's reasonable. Everyone does it that way, right? Well, say you're doing a filter stack. Let's say, for example, your TSF is a filter stack. You deposit it. Some of it's not compacted in some areas, and it's not saturated initially because you've done a decent job of filtering the tailings. For example, that's this red element right here. Okay, not saturated. But in this, what might happen in a filter stack is you might then put 50 meters of tailings on top of that before it subsequently saturates owing to either a rising phreatic surface or combined with the decreasing void ratio and therefore increase of saturation ratio. So two things are going to happen there that could make it saturated. What's quite different here is this is now happening under, pick a number, 500 kPa, for example. A quite different situation to the moist tamping procedure, which we almost always use, and which has actually no real field scale logic to it. It's just something we've always all done. So what happens if we were to do our testing like this, for example? Well, this is that same, red is tracing that test I showed you previously, where we did the saturation procedure at 20 kPa, and we ended up here. Blue is where we apply a cell pressure of 300 kPa as an analogy to maybe a lot of overburden pressure before the saturation process, and then we saturate it. In that case, we end up at a void ratio of 0.72. Now, 0.06 might not seem like maybe that much difference, given a few things, but that is a very big difference in terms of what the brittleness you might infer for a particular sample. If you shear those two particular tests and compare them, these are the responses. Now, actually, the brittleness index isn't the thing that changes probably the most dramatically here. It's more the post residual strength and the peak strengths are both dropping, but the brittleness index is changing as well. So this is maybe seems like a very nuanced lab thing that's almost irrelevant, but red is what people are going to produce 99 times out of 100 if you just send some tailings to a lab and say, can you do the testing for me? How brittle is it? Okay, red is what the brittleness index check is going to give you. But there might be situations where blue is a much more representative scenario for in situ. So just keep an eye on that. Is what I'm making in the lab analogy to what's happening in the field? Is it reasonable? Is it the same state, the same history? Those kind of things are important if we want to use this framework. Now, what's really important is if you do this, gray is the test done in the conventional manner, saturated at, say, 20 kPa. Blue are tests that each one of those is saturated at the stress at which I'm showing it. And then you'll see the brittleness index, while it does decrease with increasing effective stress, is still far, far higher at a much higher effective stress than the test done in a conventional manner. So while, yes, brittleness index is decreasing, this line, which represents a brittleness index of 0.4, which is a pretty good ballpark of when flow failures do and do not happen, we're still seeing results above that line, indicative of potential flow failure, even at 1,000 or 1,400 kPa. So be careful with conclusions of, things become less brittle at highest effective stress if it's a situation where that might not be the same history as what you're seeing in the field. Now, a second thing, similar topic, but perhaps even more scary, is subaqueously deposited silt tailings. Okay, now you might, if you look at my publication history and like some of the stuff I post on LinkedIn, I'm obsessed with this particular topic for a reason that I think is good, and that is that while this photograph here shows a decant pond, at which you may say that's not relevant for stability because it's a kilometer from the perimeter, what you often find in TSFs is that the part of the TSF that controls stability was probably deposited like this in 1985 or 1990, very close to the starter embankment. Okay, early in a TSF life, it's much harder to control the pond and have those beautiful thin lifts, and there's topography issues, and it was maybe a different era in some places in some times in 1985 or pick a year. So this kind of deposition can generally make the loosest possible condition that we know how to prepare. And it's looser often than we can prepare in the laboratory, which we need to be really cognizant of. This is an example where we've tested material from a place that was deposited like this. We measured the critical state line on the sample that was recovered, and then we compared that to the void ratio of the samples brought up in tubes. Now, we're not testing this in an undisturbed manner. That's not going to work for this, and we'll talk about that later. Testing, as an aside, testing tailings that you can't test or can't obtain undisturbed samples of, but pretending that you can, is probably the single biggest issue with trying to use brittleness index. If you do that, your samples will be heavily disturbed. They'll probably be dilative, if anything, and you'll come to very erroneous conclusions about brittleness. So that's almost a separate issue. But the main issue here is that even if you're coming at this with your moist tamping hat on, these open white circles are as loose as I could make this particular material. Those two black squares are what the in situ void ratio measured by the tube water contents is suggesting, and green is what the CPT is estimating based on a semi-empirical correlation, which is not perfect. I'm not saying any of that's perfect, but I'm saying that when the green and the black squares align, you really have to ask yourself a question that, do you want to dismiss this? I've recently ran a poll on this particular topic because I'm so kind of interested by it. The vast majority of engineers who seem to have had lived experience in this space agree that this is possible, or at the very least that they're not sure it's possible, but they certainly wouldn't dismiss it if they're an engineer of record, and they're the one who's going to suffer if this is, or that's maybe definitely the wrong word, if they're the one who's responsible for this particular TSF. So I can't see that this isn't so, and I certainly have evidence that isn't so, but this stuff up here is a lot more brittle than any of the moist tamp samples we could prepare in the lab, because the looser something is, the more brittle it is, okay? So be very cautious with conclusions drawn on lab tests in isolation without linking that to some kind of field scale response. There seems to be evidence that places that are subaqueously deposited are often the culprits for triggering. TVA Kingston, which not a TSF, but very similar. The area that seems to be where the initial failure happened is an area that was subaqueously deposited through water in the early stages of the facility, okay? The siltiest particles deposited in a subaqueous manner in a relatively still fashion. That seems to be where the trigger occurred. Feijiao, if you look at photos of this TSF, historically, you see things that you don't want to see on any upstream raised TSF. But again, there's a suggestion when you look at the CPT results and how the panels have examined this tailings, that it's very loose, and everyone seems to feel that it did exist in very loose states, looser than could be created in the lab. For example, in the first of the two panels, Robertson et al., they're indicating that about half of the fine tailings in situ are looser than any of the samples they can prepare in the laboratory. So they're just using that as a matter of fact outcome without because I don't think it's that controversial either, that subaqueously deposited tailings like this could definitely end up looser than you can make in the laboratory. So I see lots of people, incorporating this into their work without any controversy. So I don't think it's hard to argue against it as a phenomenon, I think. Tamping procedure. I know I'm going to stick with the lab. One more thing in the lab. If you prepare samples in the lab, you might prepare them loose. Typically, that's what I would recommend doing, as loose as you can, very light tamping, and then consolidate them to a particular state and then shear them. You might end up in situations though where you want to maybe make it a little bit denser, or you want to play a couple games like that. So you can actually tamp it to here. You could take a hammer or a static load cell and tap it to here, for example. That may or may not work at making it a little bit denser. Depends on what stress you're going to consolidate to, other things like that. But it's also possible, for example, if you play some games to get a result you want, to have them end up at the same state parameter. Let's say you want to write a paper on the topic and you want to see what effect this particular type of compaction has compared to a very loose moist tamping, okay? Well, the blue sample, they both have the exact same state parameter within the accuracy that we can measure this. And this isn't just a single test. We've done this a bunch of times. Blue is the response for the sample that was tamped dense, and red is the response for the sample that was tamped very loose. So both seem to be going to the same critical state line. I mean, I'm cutting this off at 15% for clarity, just for showing. There's no evidence they're not going to the same CSL. Therefore, they would have the same residual strength ratio. But the peak strength for the densely tamped sample is far higher, which makes complete sense. It's got an over-consolidation ratio, in essence, based on either a hammer or a static load cell, depending on however you made it dense. So just be cautious. I see this happen all the time. There's no real reason to do this. I mean, moist tamping is already probably far enough away from the fabric of subaqueously deposited tailings anyway, or hydraulically placed tailings. So don't go make it even further away with a hammer, okay? Would be my main recommendation. If you want to get a little bit denser, like let's say you actually wanted to get a state like where my red pointer is, there's a lot of other ways to get that other than using a hammer. You can tamp it a bit wetter, you can vibrate it, using small cyclic loading. There's a lot of things you can do to get there without a hammer. So just consider those. Ignoring the quasi-steady state. This is something I'll go through very briefly because it gets a bit heavy into the maybe cell mechanics, but I think it's something that I see happen quite a bit. And that is ignoring the quasi-steady state. Okay. If you look at the liquefaction case history database that Jeffries and Bean collate in the state parameter framework, you'll see that some of those case histories have a state parameter of 0, plus 0.02, minus 0.02. Now, if you think of things tending towards the critical state line in a monotonic manner without any real, just whiteboard critical state cell mechanics where everything goes to the CSL directly there. Something liquefying with a state of negative 0.02 makes zero sense, makes absolutely no sense, because how would that liquefy if it's going to go to the critical state line and dilate? What you see is when you shear samples of some materials from near or on the critical state line in that kind of neighborhood, they exhibit what we call the quasi-steady state. They contract initially, sometimes a significant amount, then they start to dilate back to the CSL. So no one's suggesting that critical state cell mechanics isn't valid with this kind of test presentation, just that the small to medium strain behavior might not be what you expect from what I would call whiteboard critical state cell mechanics, where everything you're drawing a bunch of arrows and they're all going to the CSL. Now, why does this matter? Why is this not just an academic detail? Well, when you look at the test results now, say, for example, in all three axes, and you see this particular material hits a peak strength at about 0.01 strain, very small strain, drops down to a quasi-steady state with a significant strength drop. So it's very brittle in that way at 4 to 5% strain. And then it starts to dilate, okay? So again, no one's suggesting that this isn't going to eventually dilate to the critical state line at the end of the test or at the end of its projected life. Now, in a triaxial device, we've usually got 30% strain to work with. So we're not going to get there with this particular sample. But I'm not suggesting we can go there someday. Okay, again, why does this matter? Well, think about this brittle strength loss between 0.01 and 5% strain, okay? Now that's happening in an element test that I can control easily. It's strain controlled. Everything's easy and controlled, and the sample's not going to fall off the table or lose control, okay? What about if that particular response is going to happen here in a slope, which is stress controlled, okay? Slopes, real life, is stress controlled, not strain controlled. The reason we do lab tests strain controlled is. It's easier. Machines like to work that way. We can do stress control tests, and they're very valuable to do those types of tests to demonstrate, like in videos and stuff, what liquefaction might look like. So they're very useful. But if this particular slope, for example, is loaded with the never wallways or whatever it might be, and it causes that element there to have this response, have a peak at very small strain, drop to a very much lower strength, but then it may want to dilate in strain terms or in an element test terms. But if this soil here has gone 10% strain before it even starts to slowly regain strength, what's happening to this slope? The slope is probably gone, or there's been such significant deformation that it's probably already maybe lost freeboard, or bad things have happened, to put it that way. And the further point might be that this dilation that we see in an element test probably might not even be, we might not be able to count on that in a field scale scenario, because the slope is moving, it has momentum, there's vibrations happening, potentially small amounts of partial drainage that prevent dilation. So we can, even if we could count on this, it wouldn't matter anyway. So this is why the concern I have here is that I see brittleness be calculated with this value, not with this value. I would strongly argue against that, and I would suggest that if you see quasi-steady state behavior, assume that is your minimum strength that you're calculating with and you're working with. There is a lot of people mentioning this in the literature over the past 30 years, but it's maybe not something that's immediately clear if you read guidelines or some things that might be the case. So if you're interested in that, I would dig deeper on the quasi-steady state if you have a chance and are interested. And if you actually, and not to, I mean, the Jeffries and Bean textbook, of course, you should be your first point of call if this is your area of interest. But all these case histories that they've inferred, and some other people have inferred, like they are on or sometimes just a little bit loose or dense of the critical state line, which makes zero sense if you just are doing what I call whiteboard critical state soil mechanics, where everything just tends to the CSL immediately. Okay, makes no sense. Now, there is uncertainty in a lot of these things for sure, in terms of like exactly what state they were and exactly what liquefied strength they were. But I don't know anyone that disagrees with this conclusion that things on or even slightly dense the CSL can exhibit flow liquefaction, and that the quasi-steady state is probably our best explanation for that behavior. Now, principal stress angle. Again, I'll go quick. It's something that is more, if you're interested in it, it's for reading later, but this is something that is ignored hugely in our profession, which is not a good thing in my opinion. That is the fact that principal stress angle, that is the direction at which the largest stress is oriented, is vertical in a lot of the tests that we do, like a triaxial test. Okay, that's a triaxial test here, a kilometer from the crest. Vertical principal stress. Okay, there's other things there such as axisymmetry, but they're not really the main point for today. This little element below the slope, which is actually far more relevant for whether the slope is going to fail or not, is a rotated principal stress angle. Sigma 1, the major principal stress, is on an angle. Okay. Now the problem is that materials that are deposited under a vertical gravity field, right? Because when these tailings are deposited, they're not below a slope. They're on a flat beach. They're deposited in a vertical gravity field. The orientation between the particles that develops under that vertical principal stress is best or most efficient at resisting loads in the vertical direction. If you then go and build a 30, 50, or 50 meter high TSF behind that location, you're rotating the principal stress angle. That's then loading it in a direction that's not as efficient at resisting loads in, okay? So if you were to take only triaxial test results and map them there directly, that can be a problem, okay? This is a bit of a cherry-picked example of a particular sand we test at UWA, or test at UWA, in a hollow cylinder, almost identical. I mean, negative 0.03 and negative 0.04 state parameters are within the rounding error you can achieve in a test. One has a principal stress angle of 0, like a triaxial test. One has a principal stress angle of 45 degrees, more representative of below at the bottom of a slope. Now look at the difference. Now, no one here, again, is suggesting that these aren't tending to the same critical state line at large strain, okay? They're both going to probably go the same spot. Now, that's about beyond what we can probably measure in a hollow cylinder for experimental reasons that don't really matter here. But what does matter is if you're accepting the previous slides about the quasi-steady state importance, then this red response indicates brittleness. This is a brittle sample, right? It's losing significant strength post-peak. This blue sample has a brittleness index of 0, right? It's dilative. You would look at that blue sample and say, we're good to go. The red sample, maybe not so much. So be very cautious in some cases of directly mapping your triaxial test, for example, to below slope conditions, okay? Now, that's a really loaded statement. There's a lot to that. There are times when it's perfectly fine to use triaxial tests in a process wherein you're measuring the critical state line, doing stuff like that, and then using it in the best practice approach of Jeffries and Bean, for example, that's an appropriate use of a triaxial compression test. However, directly mapping the triaxial compression stress test behavior to the bottom of a slope and applying it directly might not be, in many cases, an appropriate use of that triaxial test result. Okay. Final one. I've got some other slides, but I don't want to go crazy. It's probably getting too late. But the last one, because I see this happen all the time, and we only recently figured this out enough to get it accepted in a Reid journal, is direct simple shear tests, and how, if you don't do them right, they can really give an erroneous value of brittleness. Okay. This is two types. This is all tests on the same material, same silt tailings, prepared using moist tamping in a direct simple shear. Now, red is preparing it. Now, I'm not going to say exactly what this is yet. Red is type A test, where we do a certain procedure. Blue is type B test, where we do a different type of procedure. Okay. So let's think about this. Red, these are all actually, in fact, these samples are actually slightly denser than these samples, yet are showing far, far more brittleness. So why is that? Well, if you go back through the history of the DSS and how the constant volume procedure within the DSS is used, what you'll find is it was originally the most strongest evidence for it are for dry sands, which have no matrix suction of relevance, or saturated clays. People have done all these fancy experiments to prove that the constant volume technique in the direct simple shear works and is applicable, and that's good evidence. But the problem is that evidence is very specific to the types of tests it was done to or developed with. We are often caring about things like silts that we want to prepare loose, and we might use moist tamping. Okay, the conventional flushing procedures in a direct simple shear will not achieve 100% saturation in most cases. You might be like 80%. 80% is the range where matrix suction is playing a role in a silt. You know, a lot of silts, 80% saturation, there's going to be significant suction. Maybe suction hardening with it, which changes the critical state line. But don't get bogged down in that. But the long story is, if we improve the saturation. So blue test, we flush the samples with CO2, which is not at all a conventional DSS procedure at all. And then we use back pressure. You can only get about 10 kPa back pressure, say in a conventional DSS, at least that we had. You maybe could do a bit more. Far, far more brittle response. And this has been a big issue in DSS for a while, because I've seen a lot of studies where the DSS isn't showing as brittle response as a triaxial, which doesn't seem to make sense if all that stuff about principal stress angle I just said is true. Now, there's a few reasons for that. The DSS isn't measuring true shear stress. It's measuring horizontal shear stress, which has other nuances. But that's a side issue compared to this main show, which is that testing samples that aren't fully saturated can give you a very erroneous indication of brittleness, even in the constant volume DSS device, which is kind of designed to not suffer from that or not have to worry about saturation. But actually, it turns out you do for a lot of the materials we care about. I'm going to stop it there for time. I've got some more. We can talk about that another time, perhaps, because I know it's getting late, and I want to, have a reasonable time frame.
We probably can go slightly longer, Dave. Okay. Perhaps we've only got one question so far, so maybe let's address that, and then if you want to share a few more slides, we can jump back in and see if some more questions come up, if that's okay.
Yeah, sure, no problem.
So the only question posted at the moment is, should we not be looking at the brittleness in terms of state pressure index? Wang et al. 2002.
Yeah, I think you're referring there to one of the pressure normalized versions of state parameter. I'm not a huge fan of those, but just largely because I find state parameter easier to work with, and more of the kind of things I look for are framed in that, like, empirical correlations, which I know you could also calculate them in state pressure index, but or modify what exists to that level. But personally, I don't use that. But that doesn't mean that I don't think you couldn't look at that and do good things with it. So I don't want to, Gregor, I don't want to dismiss it, but it's not what I've been primarily using. Okay. So maybe that's not a good. That doesn't answer the question much, but yeah.
No, thanks.
I think there may be actually, the more I think about it, so there could be some correlations of value to be developed using that. I'm just never been a huge fan of the derivatives of state parameter that bring in other factors.
Mm-hmm. Did you want to jump into a few more slides? And I suppose for everyone, that will give you a chance. If there's anything you want to ask, we do have a little bit of time for questions. So put them up and we will ask at the end. I'll hand back to you, Dave.
Okay. If we have to keep going, then sure. Okay. Yeah. Next one. Oh, sorry, this is just a state diagram of that particular plot. Now, what's interesting here is red is those samples that were saturated using conventional procedures. They don't seem to tend to the critical state line derived from triaxial tests. The blue ones, well, within the accuracy at which we can measure mean effective stress in a DSS, which isn't great, they're going much, much closer to the CSL. Because actually, whether the CSL is unique between load angle and principal stress angle is probably somewhat controversial. I don't think the evidence arguing against it is that strong. And when I look at things like this and the work Ricardo's doing with the hollow cylinder, I don't think it's the evidence is that strong. I think there's a single critical state line, regardless of load angle or principal stress angle. But anyway, that's again, maybe a slightly academic detail. The main point is that if you want to measure brittleness from a DSS, you want to make sure it's fully saturated, which is either going to be involving CO2 flushing or potentially using a confined type simple shear that has a cell pressure. That has its own nuances that are important for the tester, but maybe not the key for right now. And if you were to plot, for example, state parameter for those tests against brittleness index, let me bring the pointer back. Let's say you took a bunch, these tests in here are using conventional saturation procedures. These tests up here are using either a DSS with better saturation procedures or other things like a confined simple shear or a hollow cylinder. So yeah, we would expect a trend between brittleness index and state parameter, or a state pressure index as well, for sure. But the fact that these are way higher at a given state parameter is what's scary, okay? Because you might be saying, oh, in situ, I think I've got about 0.1. I think my brittleness index then is maybe 0.3, which is going to be a very different conclusion to a brittleness index of 0.8. In fact, that's going to send you on a whole different journey in the ICOLD guideline of, some of your factor safety criteria, things like that. That's going to be different depending on how you prepare that sample. So just be cautious with how you get that data from a DSS for brittleness assessments. Another one. Now we're going to move. Maybe if you're not if you don't like tailings lab testing, you'll probably be glad that we're moving away from that. The vein shear test. Let's switch to that. That's a nice in situ test. It doesn't require. There's no issue with much less issue with sample disturbance because we're not carrying samples back to the lab and having them become dilative on us. But what you want to be careful of here is that most vein shear test standards were originally developed for clays, and even when they talk about drainage, they're worried about drainage for the peak strength measurement. Okay, so that's important because the longer you spend with a vein in the ground, the longer you spend rotating a vein in the ground, the more likely there is that drainage is going to play a role. Now, if drainage becomes a factor, it's going to cause the strengths to be higher than you want, or higher than they would be in reality. Okay, this is an example. Now, this has been shown. A number of people have shown this for peak strengths since probably the last 10 years, and people have recently published some ideas for, suggesting how we might update standards to deal with this. But actually, it's post-peak strength where I'm most worried about it, and that this is a result for a vein test in an iron ore tailings, PI20, 80% fines content. So somewhere where we would typically say, okay, a vein's going to give us something here. And I think the peak strengths are right for sure, because we rotated a bit faster than usual in order to try to maintain undrained conditions. It drops. I mean, this is a brittle, there's brittleness here for sure. The important thing to note here is that separate of the scatter from, friction of the rods, this starts to go up. And you could say, oh, maybe that's just increasing friction or something from buildup. Well, I don't think so in this particular case, because if you run the calculations on when drainage is likely to start playing a role, it's right about there. There's actually what's not appreciated enough is there's a pretty good framework out there to calculate based on consolidation properties how soon after the start of vein rotation can you trust the results before drainage starts to kick in. So it's a very simple analytical calculation to do. And when you're doing a CPT investigation and then switching to doing the veins right after, you should be doing that calculation. It's like 15 minutes on Excel while you're sitting on a CPT rig. So you need to be doing that calculation. Otherwise, you could be wasting a lot of your client's money. This here, I'm talking about so what's happening here is drainage is starting to probably reduce the strain softening or strain weakening process because you're having two things counteracting each other. On the one hand, this is probably, if you've done a perfect test with no drainage, this probably was going to go lower and stayed lower. But because of drainage, we're not getting to see that fully. So we actually have evidence from site this is actually probably lower. Okay, but you're not going to pick that up. You might even do the calculation that says the peak value is okay. But in fact, this value, which is maybe the most important value, might not be right because of the influence of drainage. Okay. Now, this is kind of getting to the nuance of post-peak strengths, but I see this value be reported erroneously a huge amount. Okay. it's very common for people to go out there, take a vein and say, oh, we're going to use the vein to improve our correlations, and then not rotate it fast enough, get values like 0.4 and say, oh, well, that's quite, 0.4 is a very different situation to 0.25 or something, for example. But they don't do the calculation as to whether that's drainage or not. If it's if the vein is partially drained, the results are largely meaningless. Okay, so be very careful using the vein test to help infer this. It's incredibly valuable because we get an in situ measurement of peak and residual, or or remolded, depending on your preference there. But it's only valuable if the data is undrained, and it's only valuable until it starts becoming partially drained. Okay, we're using it for undrained purposes. Now I know people are looking at it on the whole other end of the spectrum, where they test in a fully drained manner. That's a completely different kettle of fish. So that is maybe worth looking into, but that's not what we're doing in a typical vein test. We're typically assuming we're getting undrained strengths from it. It needs to be undrained for that to have any validity. Okay. CPT partial drainage. This is another thing that comes up a lot. Most of our really good correlations, like the cavity expansion, or not correlations, methods, the cavity expansion solution for Norsand, for example, or some of the other like Mason's full-scale cone modeling, or the Simney team's full-scale cone modeling on the undrained side, those things are for drained or undrained conditions. However, many tailings, if you just go out there and push a probe at 20 millimeters a second, is going to be partially drained. It's almost probably the default scenario for a lot of tailings, is you're going to get partially drained conditions. Now, partially drained conditions, while you're always going to want to do that first probe to figure out, to use your get an IC value, do your kind of semi-empirical stuff, because that's all based on that kind of standard speed. If you're going to want to get cute later and do things like cavity expansion, for example, you want to have either drained or undrained probes. Okay, it takes away a huge area of uncertainty that partial drainage adds, because partial drainage is very hard to know where you are on the spectrum of partial drainage. It just makes everything more complicated. Now, almost every good CPT contractor these days, if you say to them, I want to push at 100 millimeters a second or want to push at 1 millimeter a second, they will happily do that. They've all invested a lot in the last decade and more to have these capabilities. So don't go out there and do a whole investigation getting all your results at 20 millimeters a second if it's all partially drained. Of course, do your first tests that way, get a feel for things, but then maybe decide to do some fast, some slow, depending on the situation and what you're trying to achieve. This is an example from a paper that we just, a former colleague of mine, Kyle Smith, and I put together. We just wanted to look at what effect would it have if we had a partially drained CPT and we did the undrained cavity expansion. So assuming things were undrained, even though they weren't, did the drained cavity expansion. So assuming things were drained, even though they weren't, and then compared that to in situ tube water content derived state parameter. We get about this value here. So the two triangles are probably what's closest to being right as far as anything is. Green is what you're going to get from that result if you assume it's undrained, and blue is what you're going to get if you assume it's drained. Now, the Plouffe method, which I know, there's plenty of criticisms that can be leveled against the Plouffe method, but you can put in a site-specific value and at least plausibly works in partially drained conditions for whatever else it's worth. So it's actually not agreeing or disagreeing too bad with the in situ tubes. So it's probably got a state parameter about 0.1. If you'd assumed undrained, which probably would have been the base case assumption here, you'd have got 0.05. And if you'd assumed it was drained, which would have been quite a bit of a stretch perhaps, you'd have got 0.4, which you probably would have thrown out because you would have said it's too loose, that's not possible. So just be very cautious here when using partially drained CPT result data for this kind of thing. And a final one, sample disturbance. Sample disturbance is probably actually the simplest thing to understand and the most common way that brittleness gets messed up. This is your classic clay sample disturbance figure, okay? The NGI, Scandinavia's done a lot of work, Quebec's done a lot of work on this kind of thing. What effect is there if we go out there with a not great sample, like a 54 millimeter sample with a dull cutting edge, compared to a 75 millimeter sample with maybe a really high quality cutting edge, compared to like a mini block sample, where you take out a big block and you're in the lab, you're carefully extracting samples from that in very controlled conditions. And it goes beyond just sample diameter or the sample type, Shelby versus fixed piston, all that stuff. That's not really my main area, but I just know enough to know to be careful that this block sample has a very different brittleness profile to these other two samples. It's a very different brittleness index you're calculating from that. And it's a very different, qualitative speed at which strength is lost post-peak. which is going to inform your thinking about, are we going to have warning at this sub, seeing this fail, all that kind of stuff. That block sample is responding very differently to these, to particularly the 54. Okay, so be very cautious with that, because this block is probably the best we can do and the closest thing to reality. I see even today, I see this kind of thing. Oh, we'll take undisturbed samples, 60 millimeters, 55 millimeters, they'll come back, they'll trim them, consolidate the same effective stresses in situ and get not a brittle response. And then either one of two things happens. Either they say the tailings aren't brittle and they use the result, which is probably the worst outcome, or the medium outcome is they say, oh, the CBT is saying it's way, way weaker in situ. Why did the lab and the CBT never agree? It's all so terrible. Well, I guess we'll use a CBT because the lab testing can't be trusted. In which case, that's 50 grand probably down the drain. And then it creates this whole narrative that the lab and the CBT never agree and it doesn't make any sense. It's all too uncertain. Well, maybe that's because the samples are heavily disturbed and it's not the fault of anything. They're not aligning other than the disturbance and the increase in density. So just be very careful deriving things directly from those the responsive lab tests on undisturbed samples. The base case for tailings is we're not going to be able to get undisturbed samples. There are, particular tailings where we can if we do a good job, we can, but they're not the majority. They're not the base case. And even then, you need to be very cautious how you take those samples and treat them if you want that stress strain response to have any meaning with in situ. Okay. I think I'll call it there.
Okay, thank you, Dave. I'd love to selfishly let you speak all night because I'd be happy to listen, but I know you do have a job to go to in the morning. No further questions at this stage. I'll just check the Q&A column. No.
Oh, sorry, everybody. I was hoping for, anyway, that's not a good sign.
I thought you were going to get more too. Well, we'll let you off the hook easily for tonight. I'm sure lots of you are in contact with Dave, and he's a common attendee at conferences and different events about the place. So anything comes to mind, I'm sure you'll be able to find him soon enough. Thanks, Dave, for your presentation once again. That's going to be it for me. But before we close, I just want to hand over to Matea to share a few messages about the ICOLD Young Professionals group, and also please bring us to a close for today. Thank you all.
Good morning, good afternoon, good evening, everybody. I'm gonna be quick. I'm not even gonna share my screen. I'm just gonna say a few stuff. First of all, I'm gonna say thank you to the moderator, Jared, to the presenters from Australia. I know it's very late hour for you, but we really appreciate your participation and also the support of the Technical Committee on Tailings and Waste Lagoons in helping us with these webinars. There have been all around the webinar at least 160 attendees all the time, which will be one of the best viewed webinars live. So what you have presented apparently has a great interest among the young professionals. So just before we conclude, I would just like to say that the ICOLD Young Professionals, who are aiming to organize more webinars like this. So I would also like to say thank you to all the participants. And to everybody participating here, we are very open to see you next time at the next webinars, and also very open if you have any suggestions on future topics on the webinars. Either you know somebody, either you think you would be a good presenter, get in touch. We are constantly seeking new people, new power to help us. The webinar that is live at the moment will be available online on our YouTube channel. Just give me 2 days to post it online. Also, all the previous webinars are available to watch them later. And with that note, I would just like to say thank you again to everybody. Have a nice rest of the day. Have a good night, and see you next time.
Everybody, thanks.